I think it's recording now. Now, sometimes I simply forget about these things. So if any of you see that it's not recording, I ask you to please let me know that it is not recording, so that I will know. Okay, so fine with everybody. It is recording now. Okay, now I'm going to share my screen. You should be able to see my white iPad. You see it? You see me writing?
Mm-hmm.
Okay.
Yeah, we see it.
Very good. That's how we're going to do it. I'm going to do a share screen. I have an iPad here, so I'm going to share the screen with you. I'm going to write down on the iPad, and hopefully you also will be able to see me. And of course, I do want to encourage you to ask questions. So let's start by the basics. I mean, or maybe before even starting the basics, let's say a few words about the structure of the course. So again, this is, to the best of my knowledge, this is the first time that this course is given in Bar Ilan. Certainly the first time that I'm giving this course in Bar Ilan. It is going to be similar in content to the courses to the course with the same name that is given in Tel Aviv University. I was consulted with some of the people there, and they gave me some of the material, so that you'll see that especially when it comes to the tutorials, it will be pretty much the same, so the same content. There will be lectures. Lectures are held on Tuesdays. Writing down Tuesdays, 10 to 12. And then we have another meeting on Thursdays. That's 2 to 4, sorry, 2 to 4, but 1 hour is considered to be a tutorial. So it's 14 to 15 is a lecture, and 15 to 16 is a tutorial. Now, of course, one of the problems that we have is that I do not really have a tutor, so I will be your tutor, which means that there is a designated tutorials which are complementary to the lectures that we're going to learn. But I may take myself the freedom to slightly shift the times between the lectures and tutorials, so that when we're finishing subject, then I might take the extra time on Thursday for the lecture, and then I'll do the tutorial on Tuesday or whatever. Okay, so I'm going to be some flexible. If any of you have any problem, then of course do let me know right away. Now, homework will be given every week, basically nearly every week. Okay, that's the plan. Not necessarily every week, but based on how much we're making progress. But the idea is to give homework roughly every week. You are supposed to submit the homework. They are going to account for 20% of the final grade. And the final exam would be 80%. Now you do have to submit the homework in time. If you do not submit the homework in time, in principle, that homework does not count towards you don't get credit for these homeworks. Okay, don't come to me at the end of the semester and tell me, oh, I can submit now, etc. If you have any trouble, any problem submitting the homework, you tell it to me in advance. You tell me, okay, I cannot do it this week because something, and you ask for an extension. Now, if you do it on time, then most likely I will give you an extension. I'm pretty flexible. I mean, make it a reasonable extension. Don't come to me and tell me I can only submit that next month. But if you have a good reason, then generally there is no problem. Don't make problems, then there will be no problems. But if you come to me afterwards and tell me, oh, can you please accept it now? In retrospect, I will say no. Okay, one more thing, which is very, very important for me, is that I give equal treatment to all the students. So I don't give any discounts to one student, which I don't give to others. Either I give to everybody or I give to or I give to no one. And the reason is sometimes I hear students that come and say, oh, please, I have special circumstances, blah, 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 blah. If they're really special, you come to me and tell me that in advance, not afterwards. Okay, that's very, very important. Don't come and say, oh, why can't you accept, etc., etc. Okay, simply, you know, simple and basic. Okay, so it's all here and it's recorded. Now, unfortunately, as you all know, we are meeting via Zoom. Again, those of you who were not here, I do ask you to please open your cameras. It's for me, because it is much, much nicer for me to see your faces. I don't care if you have a mess afterward. I don't care if you wear your pajamas. It simply helped me, and it's very helpful also for me. When I look at your faces, I can see how easy it is for you to follow. Of course, I very much hope that the situation will get better so that towards the end of the semester we could meet face to face, but it is not up to me. So in the meantime, we'll simply continue like that. Do you have any questions on everything I said so far? No questions? Again, there are several of you who did not open your videos. Please do that. Okay, so this is a course in particle physics. So the first question that we're going to ask is, what is particle physics? I give it up to you. What is particle physics? Come on. Nobody knows. Nobody wants to define. Yeah, go on. Simply speak, because I don't have your names. I don't think you're, just check out that you are not muted. I actually ask you not to mute yourself unless there is some noise so that you can speak. Okay, I see somebody is speaking, but I cannot hear you. You may want to write down. By the way, I did not ask you, can you all hear me?
I can.
Yes,
you can. Okay, good. Now, if there is any connectivity problem, I mean, I'm relying on a local internet. It's generally good, but you know, if something goes wrong, it might disconnect. Then just wait, and I will try to reconnect as soon as I can, of course.
In regard to the question,
yes.
For me, I think particle physics reminds me of scattering, if it's connected.
Remind you of scattering, okay. For me, scattering reminds me of a billiard game that I used to play when I was younger. Okay. There is a good reason why it reminded to you. More? Oh, what did I do? Okay, go on, more. Okay, so particle physics is a branch of physics which tries to answer possibly the most fundamental question, which is, what are the laws of nature in their most basic form? So in that respect, it's a continuation of early theories, such as gravity, relativity, quantum mechanics, etc. So it does try to attack the most interesting, the most fundamental and basic laws of nature. So, you know, this is a very big and you can say philosophical question. So on the way, it tries to answer several, let's say, smaller questions. So if we, you know, if you take it and make it into simpler questions, then these could be formed in a way of asking, what are the fundamental ingredients of matter? Right. What are the basic forces, the basic interactions that act among them? What are, you know, at least some of, you know, the principles that lie behind these laws of nature? Why are they there? You know, I heard once an excellent talk by Mario Livio, who was speaking about Newton's gravity, and there is something which is amazing when you think of Newton's laws of gravity, right? As you know, two massive objects attract themselves in a force that is proportional to the masses and inversely proportional to the distance squared, right? The issue is the square. You know, it's just to the power 2. 2 is a very simple and nice and great number. Why is it 2? Why is it not 2.145, for example? Now, more interestingly, you know, definitely in Newton's time, the observational evidence that there was not enough to discriminate between 2 and 2 point something. But Newton came up with a 2, which is, you know, nice, simple number. Why? Why is the laws of nature so simple?
Maybe it's connected to what Gauss did with electrostatic force.
That comes way later, way after Newton. Remember that Newton did his theory in 1687, right? Where he publishes that. Maybe he published it even slightly earlier. And Coulomb was from the 19th century. So more than 200 years, about 200 years later. They knew about Newton's law. Newton did not know about electrostatic. But the question is the right one, right? Also in electrostatic, it's a very simple, right? But why is that? Did you ever think of that? Why is that 2? Why not, you know, 2.0769? So the next question is, what are, you know, at least part of the principles that lie behind the laws of nature? And finally, again, related to the example I just gave you, is, you know, how are the answers to these questions affect the world we live in? In other words, the universe. How are the answers to these questions affect the evolution of the universe? Now it is here that there is the connection between particle physics and astronomy. Specifically, there is a branch of science, astrophysics, known as cosmology, which studies the evolution of the universe in the large scale. So we're not going to do that here. This is a special, this is a designated course in cosmology. We're not going to study it here. If you want, I encourage all of you to take the course in general relativity, which will be taken in second semester. And then in the end, we say a few words about cosmology, but really just an introductory part. Here, we're not going to say anything about that. We're going to focus on the first three. So, when you think of it in that sense, then the particles, right, the ingredients of matter, they're not even the main subject, right? It's just a tool for us to study and understand the basic principles of nature. Okay, you all with me? Okay, very good. So, just to have a little bit of the descriptive, right? The description. So you might have heard of nuclear physics. So when we speak about nuclear physics, right, physics of nucleons, this is from the historical basis of particle physics. This is basically how it started. So this is a historical basis of particle physics. Today, it is considered to be a branch of particle physics. Okay. We do use, not me, but scientists that deal with that do use nucleons in laboratories to study various aspects of particle physics. In particular, things such as the strong force, which is the force that binds the protons and the neutrons together in the kernel. Conservation laws, etc. Now again, let's say a few words about the purpose of this course. As you can understand, just from these very basic definitions, particle physics is a very broad and deep subject. It is definitely not a subject that we can cover in one course, which is even aimed for undergrads. It deals with very small particles, naturally. So that means that the laws of quantum mechanics are the laws that hold. Okay, so particle physics, we have small particles. We need to have to use quantum mechanics. Now, I do want to ask you a question at this point. How many of you are second year students? Please raise your hands. How many of you are third year students or above, namely masters? Seeing some. There are some that I did not see your hands raised. If you did not open your camera, then obviously I cannot see your hands. But, okay. Okay? Because I assume that you don't know quantum mechanics that well. So I'll try not to rely too much on your knowledge of quantum mechanics, though of course it is needed. Now at the same time, a lot of the particles that we're going to deal with are often relativistic. And when they're relativistic, then we need the formulation of relativity. Relativistic, namely they move at speeds which are very close to the speed of light. So obviously we need relativistic mechanics. Fortunately, we only need the formulation of special relativity. We don't need general relativity, because then I would not be able to teach this course. So special relativity. Which I will denote by SR. Special relativity. There is still no complete theory that merges general relativity with quantum mechanics. But there is a theory that merges quantum mechanics and special relativity. Who wants to tell me what's the name of this?
QFT.
Which one?
Quantum field theory?
Yes, quantum field theory. So when you merge these two together, you end up with what's called quantum field theory. QFT. And this is the theory that lies behind, that forms the theoretical basis of particle physics. Now, I'm not going to teach you quantum field theory. This is something that is being taught in first years of master's degree. So I cannot assume that you know it. And that puts me in a situation which is, I have to admit, this is something inconvenient for me, because that means that a lot of the concepts and a lot of the calculations, like we're going to do Feynman diagrams, for example, I will tell you the rules, I will tell you how to do that, but I will not be able to give you the full explanation of why it is being done like that. And it's even worse because it's not that, okay, it's, let's take like 2 hours and then I could explain it to you. It's more than 2 hours. You actually need to take a full course in quantum field theory before we can even start explaining why things behave like that. So this is, for me, it's a drawback, because the thing that I really like about physics is that everything is, as a full logic, everything is fully explained. And here in this course, there will be things that I will simply have to tell you, look, you have to trust me on that. You have to believe what I tell you. Or mark it yourself in a box and then go and study a course in quantum field theory. And after you study the course in quantum field theory, then you go back and you say that what I told you is correct. Okay, so this is so in that sense, we will not be able to go to the full level. So if we want to go the full level, the way it normally works is that you first have to take a course in quantum field theory, and only then basically you have to take a second course in quantum field theory, which I'm not even sure if it's given in Bar Ilan. And then we can take a course in the most fundamental, in the basis of particle physics. So if there will be enough demand, then maybe we can cook up some course in the coming years. So the purpose of this course is not to replace that course. Instead, the purpose of this course is to give you a quite good overview on the basics, on the basic concepts, on the fundamentals, on some both overview. So both the theoretical overview and the experimental basis. And as you might have heard, I'm sure you've heard about the CERN and the LHC and the Higgs boson and all that. Some of the theoretical predictions are among the most tested predictions ever made by man, with the most accurate experiments that are good to many digits accuracy, more than anything else that has ever been measured in the lab. Questions so far?
I want to emphasize your point about QFT. Feynman diagrams are not taught in the master's course that you mentioned. So probably no one here really knows Feynman diagrams properly, unless someone did put himself.
Since I did not hear you very well, I want to repeat what you said. Feynman diagrams are studied or are not studied in a quantum field theory course?
No, they are not. The graduate course in advanced quantum mechanics does not cover Feynman diagrams. They are drawn on the blackboard every now and then as kind of intuition, but they're never really explained of how to derive them and what they mean and what the propagators and so on. It's not taught properly. Okay.
That is not okay.
In case you wish to teach it in the future, that will be very cool, actually.
Okay.
I can encourage
you. I will okay. Thank you for these comments. The reason why it is not done is that because quantum field theory is being used by two main branches of physics. One of them is people who study condensed matter physics, and they really, I think, I don't study condensed matter physics, but to the best of my knowledge, they use much less of that formalism of Feynman diagram, though they do use the same formalism of quantum field theory. And I think this is why it's not taught here, because it's taught by people who are experts in condensed matter. The other branch of people who teaches that are particle physicists, and then they do use Feynman diagrams. Now I can refer you to my webpage. I taught a course in quantum field theory, and I did teach Feynman diagrams. So it is on my webpage. You can find it on my old webpage and my new webpage, a course in quantum field theory. It's heavy. it's a big course, and then you can find it here. I'm not going to teach you the entire theory behind Feynman diagrams, because again, this requires about half of the semester to understand how they go to, but it is there. If you have some background in quantum field theory, you are invited to go to my lecture notes, and possibly it will be easy for you to complete it from there, at least some of the theoretical part. Here in this course, I will introduce Feynman diagrams. I will explain to you how to use them and what they're good for, but I will not be able to provide the full theory behind them. I mean, these seemingly very nice lines and wiggles and things that look like that, they hide behind them extremely nasty integrals. And there is a great logic that goes behind them and why it is there. Again, this goes to one of the beauty of physics. It has to be like that, but you have to understand what you're doing before you do it. So we will go through the Feynman diagrams, but it will be more on the descriptive side of how to use them and what to do with them, than rather how did Feynman derive them in the first place. Okay, if we speak about that, in the course's website, you might have seen I put the syllabus. I think since I put it in June, I slightly tweaked it, slightly more precise. I don't think it should really matter to any of you. It's slightly more focused by now. The important thing are the textbooks. So there are 4 textbooks that I will use through the semester. I have 2 of them on the online version. So one of them is by Griffith. It's good. It's not very difficult. Textbooks by David Griffith. Yeah, I'm sure you know David Griffith. He wrote textbooks on many different subjects. He has textbooks on quantum mechanics. He has a textbook on electromagnetism. He also has a textbook about particle physics. Again, it covers the basic things, I think. So David Griffith. These are, by the way, all in the syllabus that I posted. Another textbook is by Thomson. For me, it's a new textbook. So I started reading it only a few weeks ago. I like it. It's a good textbook. I think it takes quite good approach generally. So I think this might be the main textbook that I will be using. I mean, I'm going to use some sort of a linear combination of all these books. But the book by Thomson might be the leading one. Then there are 2 other textbooks which I happen to have with me, so I can show it to you. One of them is by Halsen and Martin. It's this one, Francis Halsen, and it's a guy I know. It's quite old by now. It's kind of a classical textbook. I think this is a textbook that was used when I was a student. I won't tell you exactly when, but it's been a while. So this is called by Halsen and Martin. Francis Halsen is one of the leading figures. He's now working in the neutrino experiment in the South Pole. You know, really nice guy. And another one, which is more, I think, on the observational side, is called, this one is by Perkins. It's by Donald Perkins. I know less about this book than I know about the other books, but I still have it. So
if you cancel the screen share, we can see you bigger, because I think we couldn't actually see the books very well.
You want me to cancel the screen share? So I can do it for a few minutes. So these are the two books. This is the book by Perkins, and this is the book by Hudson and Martin. Hudson and Martin is a bit older. Is the book that I use. They are all found in the syllabus. So you just go on the course webpage, and it's in there. Now I need to share a screen again. Let's see, there is a chat here. Okay. Okay, if you don't have cameras, then obviously I don't expect you to connect if you don't have a camera. But still do your best, you know, as much as you can. Okay, questions about anything we said so far? Questions? No. Okay, no questions? Guys, especially that we're not a particularly large group, I do want to encourage you, I don't know how to emphasize that, to ask questions. The more you ask, the more you know. If you read Feynman, you know, Feynman has several very wise things he said in his book. And one thing he said is that, you know, always ask questions. If a student doesn't ask questions, that can be because they are shy or they think that everybody else understands and they're the only one who don't understand. This is often bullshit, of course. If you don't understand something, very likely you are not the only one who does not understand. Somebody else does not understand either. And also people are afraid that people will think that they are stupid. Well, that's of course wrong, right? Nobody's going to think you're stupid. The better thing is that once you ask something and then you know the answer, and then if somebody else down the line next year or, you know, wherever you go will ask the question, then you will know the answer, and then everybody will think that you are the smart guy. So I do encourage you to ask questions, although I hope I will not be the one who doesn't know the answer. Now, it could be, but if I don't know the answer, then I'll just tell you I don't know, and then I'll go and check, and I'll come back to you with an answer as soon as possible. All right. So after this speech, do you have questions? No, then we proceed. What is a particle? So what is a particle? Oops, what happened? What happened this morning? Can you see my screen? Okay, I might have stepped on the cable.
It's back now.
You know, I think I might have stepped on the cable, so hopefully there will be. Again, I mean, there could be problems, technical problems, because of this crazy situation we're all in. Hopefully it's not going to be that bad. So an elementary particle right? Essentially, it's a basic quantum entity, which is not composed of other particles, right? It is a basic of other particles. Okay, so first it's a point-like particle, right? So zero size. Of course, it's not really zero. I mean, in string theory, particles would have a typical length scale of about 10 to the minus 35 meters. But for us, this is going to be zero. String and size is about 10 minus 35 meters. For our purposes, it's simply zero. And the second is that it has a small number of properties, right? Such as a mass, spin. There will be other quantum numbers which we will use to specify particles, right? It has a small number of properties. Right. So in that respect, an atom is not an elementary particle. It is composed of other elementary particles. But it does have, as it often occurs, it does have also quantum numbers, right? Mass, spin, etc. We can specify for an atom, etc. But of course, these properties are originating from its structure. Right. Although in everyday life, we use the term particle to describe also atoms and other bound states of elementary particles. They are not considered elementary particles, but again, a lot of the characteristics of the non-elementary particles are similar to those of elementary particles. A lot of the characteristics of non-elementary particles, particles are similar to those of the particles. Okay. So theoretically, every particle theoretically, so we said that every particle is really a quantum state, which is characterized by a quantum number. And it is described in the basis of eigenstates of the relevant symmetry operator and corresponds to a member in a representation of this operator. I know this may not sound very easy at the moment, but this will become clearer later. Describes in the basis of eigenstates ערכים עצמיים. It's clear to everybody what I'm saying? I mean, you know, as much as it can be clear at this stage. Described in the basis of eigenstates of the relevant symmetry operator. Operators. And corresponds to a member in representation of these operators. Now this has been tested experimentally, though it sounds quite abstract at the moment. I hope this will become much clearer in a few weeks' time. Questions? None? שאלות?
So to say that, for example, the electron, for example, would be an eigenstate of some operator. And then, for example, the muon would be a different eigenstate of that same operator. Is that kind of like the idea of trying to convey
Yes.
here?
Yes.
But it's kind of so it's the same set of operators that, I'm not quite how to phrase this question, but like, it's like you have a limited number of operators, but in general, you could have a lot of particles coming out, right? Because one operator can have an infinite number of eigenstates. Right?
Not so many operators, but not so many particles, but yes.
Okay.
We'll go through that. Wait, not too long, and we'll go through that.
I have a question.
Yes.
Well, the first characteristic is having a point-like position, but that's not quite described in the. I mean, when it solves the Schrödinger equation, we see it doesn't have point-like position.
Yes,
Am I
that's
misunderstanding?
okay. That is because Schrödinger's equation is part of quantum mechanics, and we are not dealing with quantum mechanics. We're dealing with quantum field theory. So the Schrödinger equation, in quantum mechanics, the Schrödinger equation is called the wave function, right? The wave function of a particle. In quantum field theory, we speak about fields. Okay.
Mm-hmm.
So a particle is really described as an excitation of a field. We will go through that in some depth. I'm not sure how much depth.
I'll try to keep listening, and maybe I'll understand
Okay.
by the end of the lecture.
Okay, likely not this lecture, because this is just sort of an introductory lecture to what we have. But in a few weeks' time, I hope this will be much clearer. I hope. I cannot guarantee again because I'm not doing the full quantum field theory here.
What do you mean when you say the representation of these operators?
Well, you find. Sorry?
I think you're referring to group theory, right?
Yes. It's a representation in a certain basis.
Together with Feynman diagrams somewhere in the not being taught.
Well, Feynman diagrams are not related to that. Feynman diagrams is something different. What I will give you as a homework for today is to read chapter 1 of Griffith, the book by Griffith. It is an historical introduction to particles, and it describes a little bit of the symmetries that people considered mainly in the 1950s and the 1960s. So maybe this will give you a little bit of a feeling, and a better feeling you will get down the line. If I try to answer it in a better way, in quantum mechanics, right, we have observables, right? When we make a measurement, right, one of the principles of quantum mechanics is when we make a measurement, then we always get a result which corresponds to an eigenstate of a special type of operators, right, known as observables, right, Hermitian operators, right? So when you make a measurement in quantum mechanics, you always end up with one eigenstate. So it's something analog to that, but in the quantum, in a slightly different formalism. I hope
yes, I'll have to wait and see.
Yeah, I'm afraid so. Okay, more. You have anything more? Okay, how do we study elementary particles? So, in classical mechanics, that goes to the first question that I asked you, and somebody spoke about scattering, right? So if you speak about classical mechanics, right? Then, if you want to study the forces between two bodies, then we can simply attach them with a rope, or with a spring, and then we can measure the force as a function of the distance, right? This is pretty much exactly what Cavendish did when he measured gravity. This is what Coulomb did. We spoke about Coulomb, but obviously we cannot do it in particle physics, right? So practically, the particles are too small, so we cannot attach them to any rope, neither to any spring. But more fundamentally, these are quantum objects. And if we make classical experiments, we get some classical result, which is really meaningless. So it will really give us the wrong answer. So we must somehow find an appropriate method of study the properties of elementary particles. So really, nearly all of the information we have about elementary particles come from 2, maybe 3 types of experiments, whose results can be compared to the theoretical expectation. So nearly all the information about particles originate from 3 types of measurements. So what is the first one?
Collisions, colliders.
Right, scattering experiment. So your intuition was wrong. We have scattering. Right? What happens? We let 2 particles collide, right? We give them energy, and we measure the probability of getting a certain result. So, if it's an elastic scattering, we can look at the probability of being scattered to a certain angle. Or if it's a non-elastic scattering, it can be the probability of the outcome of the resulting particles. This will lead us to the concept of a cross-section. It's a scattering, so simply we let 2 particles collide and measure the outcome. Which is the probability collide, I should say, collide at a given energy. So we know, or we hope to know, what is their original energy. We let them collide at a given energy, and we measure the outcome, which is the probability of scattering, or probability to get a certain result. This is one. What is the other type of experiment that we can do?
Observation from the universe, like particles flying into Earth.
I did not hear you very well. Can you please speak again?
Sorry, you could look at cosmic particles that detect them in some, you mentioned the South Pole earlier, so measuring particles that come out of space and get stuck somewhere.
Essentially, it's a scattering experiment. You're right. I'll say a few words about that in a few minutes, actually in 1 minute. Essentially, this is a scattering experiment. We have a particle that comes from outer space, and it's being scattered on particles in the Earth's atmosphere. So in essence, it's somewhat similar to that. There is an extra thing here, which I want somebody to say, if you can. A different type of experiment.
Maybe radioactive decays?
Decay, very good. This is the word I was looking for, exactly, decay. So in a decay, most particle When you think of it, most particles that we know of are not stable. There are only very few particles that are stable, which means that after some time, they turn into other particles. Okay? I specifically said they turn into. So here too, we measure the probability for a certain decay as a function of time, right? I said turn into other particles because these are particles that were not there previously. Okay, they just generate new particles. So just say, that's right, most particles are not stable. And after some time, they turn into other particles. And so we can measure the probability of a certain decay as a function of time. By the way, if you find it hard to read my handwriting, let me know. I don't know, right? If you don't hear me, if you don't see me, if you cannot read what I'm writing, let me know. I don't have a way of knowing. The third way is to look at bound states, right? Such as atoms or others, right? So 2 particles or more can be found in bound states. So sometimes what we do is just measure the masses or the quantum numbers of bound states of particles, and try to understand from that the properties of the elementary particles. Whatever. Okay. The next thing is, how do we produce particles for study? So where do we get the particles that we're studying from?
Outer space.
Outer space, right. Okay, so basically, we have the famous Einstein's relations, right? E equal mc squared. But if we are to be more precise, it's just E equal p squared plus m squared, right? P squared plus 1. E is the energy, P is the momentum, right? Which we can use for giving a lot of energy, and then we can produce either more particles or heavier particles. Okay? So the sources that we can find of energetic particles so the first, indeed, you said properly, is cosmic rays. So cosmic rays, by large, most of them are protons, but not all of them. We're actually not sure. At certain energies, we're not exactly sure what is. There are some evidence for composition change of energy. We won't get into that. So these are mostly protons that have some origin outside of Earth. Again, where do they originate is a different subject. Very interesting one. And when they reach Earth, they interact mainly with nuclei in the upper atmosphere. And this interaction produces new particles in what's called an air shower. And these new particles can interact also with more and more particles as they go down the atmosphere. Eventually, these particles reach the detector and are being seen. So they reach extremely high energies. They reach much higher energies than can be reached in man-made laboratories in CERN. I remember that a few years ago, people were afraid that CERN, when it goes to too high energies, might produce miniature black holes, etc. It's kind of ridiculous because the energies that we are seeing in cosmic rays are at least 10,000 times more than the maximum energies that we can reach in the largest particle accelerators. Okay, so let's figure out a few words, mostly protons. But mostly, not sure, that interacts with nucleons in the upper atmosphere. Can reach extremely high energies. Again, many orders of high. I'll tell you later on what energies they reach. Just that you know that it's much more than can be reached in modern man-made facilities. But of course, the problem, what is the problem?
We can't control it.
Right. We don't know where they're going to come. We don't know exactly where they're coming from. And the flux, the surface density is relatively low. So the surface density, this will be the plus and this will be the minus, the surface density is low. Historically, these were the first, I think, no, I'm pretty sure, these were the first to be studied. That goes back to Victor Hess, that got the Nobel Prize for that in 1936. At that time, he did the experiments using balloon. This one on a balloon, we took some, we did this experiment. He got the Nobel Prize for detecting them. At that time, if you go back to 1936, they knew about radioactivity, but they thought that as they go higher in the atmosphere, there will be less and less radioactivity. He went up in a balloon and he actually measured that it gets more and more, the flux actually rises. So he was forced to conclude that there are cosmic rays coming from above us. So the structure, the surface density is low, and of course we have no control over their type, energy, etc. Okay. What is the second source of particles? Where else can I get particles? I want to study particles. Where can I get one?
Yes,
Give me one.
use the decay as a source of particles. So the one hand is observable, and the other hand could be the decay, which would be a proton. Just to use it as a source.
You say, if I understand correctly, because there was some communication was not that great, there was a decay of particles. That's what you said?
Yeah, I mean, I'm guessing, but I guess you could use that as a source.
Well, the problem with that is that the energies will be too low for me, and that I need to have a source of particles that decay. So I need to have a radioactive source. Where can I get that?
I don't know, Iran.
Where?
I'm joking.
Okay, no,
maybe you can.
No, first of all, this is true. Radioactive elements. I wrote it down. This is for radioactive elements. But what would be the main source today?
Maybe you can ionize something.
I can't. I guess people do that, but it won't produce a large number. I assume. Actually, I don't know. Well, it's much simpler, right? It's nuclear reactors. We have nuclear reactors, and they are the source of particles. Again, the advantage here, of course, is that the flux is very high. You can reach very high fluxes. But the disadvantage is that the typical energies that we can get are actually quite low, right? Relative to what we want to study. Okay, so the energies are relatively low. Not enough for us to study the things we want to study today. What is the third source?
Particle accelerators?
Again, what did you say? I did not hear very well.
Particle accelerators?
Oh, exactly, very good. Particle accelerators. So what do we do in a particle accelerator? We basically are doing a controlled collision of particles. We take two beams of particles, right, called beam particles. We provide them with very high kinetic energy. We accelerate them using electric fields, essentially. And then we let them collide, and we can produce many particles at the desired location. Right? We actually can control very well today. The technology enables to control the exact location of the collision up to a micron. And then we put this collision location inside a detector. Okay? So it's designed in such a way that you're accelerating two beams, you let them collide, and you ensure that the collision occurs exactly where you want it to be inside the detector, so that you can detect the outcome of the collision. Okay, so it's a control. Essentially, it's a controlled collision. Of particles. Beam particles. Given a high kinetic energy, I said, and you produce, you control the location. So the energy are quite high, but still many orders of magnitude lower than the energies that we are seeing in cosmic rays. Energies are high, but less than in cosmic rays. The rate of events that we can get is lower than what we get from nuclear reactors, but it's still higher than what we see in cosmic rays. Right, it's somewhere in between, higher than nuclear reactors, lower than cosmic rays. But again, this is technologically dependent, and then the new technologies are continuously working towards improving that. Just one word about detectors. How do we actually detect the particles? So how do we detect the particles? It's all essentially based on the fact that when particles pass inside a material, it loses some of the energy to the material. It all goes to the same basic thing. So let's write it down. When a particle passes through a material, it loses some of its energy. Okay, so typically it is possible to measure the location where the particle was and also the energy and momentum. Now, obviously the accuracy is much less than we get from the upper limit set by Heisenberg's principle, but it's still quite good. All right, measure location and energy, momentum. Questions so far? Okay, one more thing before we, okay, a few more basic things. Actually, I'm going quite slow. Am I going too slow, by the way? Do you want me to speed up things? So this is still an introduction. When we get to more technicalities, then we'll see how it goes there. So I just want to say a few words about the difference between a model and a mechanics. So there is a model, right? Which is a specific theory that describes the type of particles in the universe. And of course, the forces between them. And we speak about mechanics, which is a broader theoretical framework. Right, so we have classical mechanics, right? And there is the law of, the Newton's models of gravity, right? So Newton's model of gravity, right? F is G M1 M2 divided by R squared. This is, can you see my screen?
We can't see your screen anymore. It's frozen.
Oh.
Right. Why? Try to reconnect it back. What happens? Okay, good. Maybe there is a reconnection here. So there is, mechanics is a broader theoretical framework, right? We say classical mechanics, right? But and then there is a model of a specific thing within that, right? So we say Newton's model of gravity is valid in the framework of classical mechanics. Same, we can speak about quantum mechanics, right? So we have classical mechanics, we have quantum mechanics, and of course, what I told you already is that for particle fields, we have quantum field theory. So we can say, I have a small table that will set what mechanics we're using. So that depends on the size of the particle and on how fast they are. So if the particles are slow and large, then what are we using?
Classical.
Classical mechanics. If they are slow but small,
Quantum mechanics.
quantum mechanics. Very good. If they are large but fast,
Special relativity.
that's right. It's relativistic mechanics. And if they are both small and fast,
Our beloved quantum field theory.
so we're here. So, okay, so this is the model, this is the mechanics that we're dealing with. Now at the heart of quantum field theory, we have the Lagrangian. It's the same Lagrangian that you're familiar with from your analytical mechanics course. Well, not exactly the same, but similar. Now the Lagrangian is going to contain all terms that are invariant under symmetry operations. The Lagrangian contains all terms that are invariant under all symmetry operations. So in that sense, it is the symmetry operations that define the model. Okay, so the symmetry operations, they are the ones that define the model. So in that sense, you might have heard, people are looking for symmetries. And that's how they hope to find new particles, right? Now we have, you might have heard about supersymmetries, etc. That is the general framework. Again, I hope this will become easier to understand the exact meaning in the coming weeks. In quantum field theory, there are a set of rules. These are, of course, the Feynman rules, which tell us how one can calculate measurable quantities from the Lagrangian. So Feynman rules, these are a set of rules that tell us how to calculate measurable quantities from the Lagrangian. So we set the Lagrangian, we set symmetries, and then we use Feynman rules. Well, we know what are the symmetry operators, and then we use Feynman rule to calculate things such as what is the decay rate, what is the decay probability, what is what's called a cross section, which describes scattering. These are essentially the things that we can measure. Now, about, I don't know, many decades of work led to what is known as the standard model. Of particle physics. It is a quantum field theory based model. So it lives in the realm of quantum field theory. That's why I said you have to know quantum field theory in order to get all the essence of where it got. And it is exactly the model that defines all the symmetry operators from which we are deducing the particles. it is a great success, as you might know. The theoretical predictions of this model are in accordance with many thousands of experimental data tests and some of the most highest accuracy. However, and this is a very important issue, is that there are clues that this is not a complete theory. So it's really only an effective theory, which is valid only at low energies. Well, low relative to some higher energies. So in a very similar way that the Newtonian theory is, we can consider it as an effective theory, which is, general relativity at low velocities give you back, and weak fields give you back Newtonian mechanics, and also quantum mechanics. If you go to the limit of large scales, that gives you back classical mechanics. So classical mechanics is, or Newtonian mechanics, you can think of it as an effective theory of systems which are contain objects that are big and velocities that are small. So the same way, the standard model, there are very good clues that it's only an effective theory. So what do I write down about that? One thing is a QFT based model that provides excellent right predictions that were tested experimentally. With an excellent accuracy. But there are clues or evidence that it is only an effective theory. That is not valid. That is only valid, I should say. At low energies. Okay, questions?
In one sentence, can you name the evidence you're referring to?
No.
All right.
No, I'll try to come up with something for next meeting. Something which will be simple to get. Sorry for that.
Perhaps I'll be more, I'll rephrase. Do you refer to results that are like, oh, we have a prediction for 10 digits after the decimal point and it only agrees to 8 digits? Or is it like something fundamental and...
No, to the best of my knowledge, there is no, this is kind of the, I would say, disappointing thing. To the best of my knowledge, at the moment, there is no experimental evidence that's saying that it is not, unless you go back to cosmology. And there in astrophysics, but then there are various results which can be interpreted in more than one way. No, it is something else, but I'm not sure that I can easily phrase it right now. So I'll just try to give you a good answer to that next meeting. Okay.
What is low energies?
Well, the scale that there is, okay, this is actually leading us to the next subject, which is quite good. There is a natural scale, which is called the Planck scale. The maximum scale that we reach is something like 16 orders of magnitude below the Planck scale. When things get close to the Planck scale, then things behave in a different way. But I cannot give you now a very good answer to the question that I was asked previously, so I'm just skipping it to, I'll answer that on Thursday. Okay, but that leads us to the next, we start to get into, we're still in the preliminary stage, but we start to get a little bit more to the technicalities. So the next subject I'm going to speak about is called natural units. So, you know, we are used to think of units which are man-made, right? MKS, right? Meter, kilogram, second is something which we define. If we were to live in a different planet, then we might have used a different system. Or even in our planet, right? Americans don't use meters, they use pounds, right? Sorry, meters, they use whatever. Miles, yards, feet. They don't use kilograms, they use pounds, etc. So in the system of units that is being used in particle physics is known as natural units. And we have several fundamental constants of nature. Specifically, there are two. So we have h bar, Planck's constant, right? It's 1.054 times 10 to the minus 34. If we use MKS unit, joule per second. And we have the speed of light, 3 times 10 to the 10 to the 8. I'm used to work in CGS, meters per second. So in the natural unit system, we take both these to be 1 and dimensionless. Okay, and as you're going to see in a few minutes, oh God, we're getting close to the end of this lecture, but we will just finish with that. This is going to give us that all the quantities are actually going to be expressed in the powers of energy. So the units we're interested in, well, first is time and distance. So do you know what is a typical distance when we speak of in particle physics? What's the length scale of an atom?
Angstrom?
1 by 1?
Angstroms?
There is something that I cannot hear very well. Can you say it again, please?
Angstrom, 10 minus 10?
Very good, yeah, it's an angstrom, that's right. That's still too big for us. What's the size of a proton?
Femtometer, 10 to the minus 15.
Yeah, very good, that's correct. So this is the typical length scale of interest. So size of a proton. It's 10 to the minus 15 meters, which is 1 femtometers, as was previously correctly stated. This is also known as Fermi, 1 Fermi.
By size, you're referring to the wavelength.
Yeah. Since the proton, as we will see, is not an elementary particle, it's a composite system, then yeah. Again, it just gives us the scale, right? Now, if we set the speed of light to 1, right, then it means that the time, right, the time it takes the light to cross a proton, right, is just the size divided by the speed. But if the speed is 1, it means that the time and length has the same units. Now, if we insist on measuring time in seconds, then the natural distance unit is a distance in which light travels 1 second. If we measure distance in meters, then the natural time unit would be the time it takes to cross for light to cross 1 meter. Now, if we're using natural units, right? Since the unit of time, in natural units, right, so units of time is energy divided by h bar. So unit of energy divided by h bar, and to the -1, right? And then it means that the unit of time is a unit of energy to the power -1. And units of energy I'm going to write in giga electron volts. So energy to the -1 is GeV to the -1. And this is a unit of time and of mass. Okay, I said GeV and I didn't specify what it is. So let's just specify that if I'm looking at energy. Obviously, units which we use in everyday world, you know, such as the joule or erg, are way too big to deal with elementary particles. So in atomic physics, we use units of electron volts. For energy in atomic physics, we use electron volt. So 1 electron volt is 1.6 times 10 to the -19 in joule. Now the number here is simply the electron charge in unit of Coulomb. Right, an electron volt, this is the kinetic energy given to an electron, which is accelerated in a potential of 1 volt. Right. Now, what are the typical energies that you reach in nuclear reactors? Do you know?
GeVs.
Oh,
sorry, in what? Nuclear what? Nuclear reactors.
Nuclear reactors.
Oh, sorry. Thought you talked about accelerators.
No, accelerators. But in nuclear physics, we're talking about KeV and MEV. We have KeV, which is 10 to the 3 electron volt, and MEV, which is mega electron volt, or 10 to the 6 electron volt. When we speak about accelerators, then we reach much higher energies. Right, we're speaking of modern accelerators. We'll be speaking about GeV, giga electron volt, and TeV. Now, I told you for your references, what was the maximum energy that was measured in cosmic rays? You know? Any guess? One,
10 to 15?
How much?
10 to 10, 15?
10 to the 15. Do I hear more? In CRs, we speak about 10 to the 21 electron volt. Now, this is the energy that you can accelerate. What we do in accelerators, we accelerate 2 beams and we let them collide. So the actual energy that they get is higher than that. But for a single beam, That's pretty much what is being accelerated. Okay, this is for about energy. What about momentum, mass? So again, for units of momentum, we simply use Einstein's relations. Right? E squared is just P squared C squared plus M squared C to the 4. Since then obviously the units of momentum GeV over C, and the mass is GeV over C squared. But since C is equal to 1, both of them have units of GeV. It's quite handy. So if I make a summarize of the basic characteristics, the basic quantities, and then the unit in SI, then the unit in the natural, so length, what is the SI unit for length?
Meter.
Meter. And the natural unit for length? The natural unit for length? I said it 10 minutes ago.
Femtometers?
No?
It's not fundamental.
No. What is the natural unit for length?
Oh, inverse energy.
Right. GeV minus 1. What about time? What's the SI unit for time?
Seconds.
Seconds. And what's the natural unit for time?
Inverse energy.
Right. GeV minus 1. Mass? What's the SI unit for mass?
Kilogram.
Kilogram. And the natural unit for mass?
Energy.
Energy. Energy. The SI unit for energy, I'm sure you remember that, kilogram meter squared second minus 2. I simply remember it as MC squared. So M is kilogram and C is just meter per second. So this is just GeV, obviously. And momentum, right, it's just kilogram meter per second. And units in natural?
Energy.
Energy. Everything is energy. Quite handy. Of course, you can proceed, right? Area would be units of length square, so it would be GeV to the minus 2, etc., etc. Okay, I think I'm a little bit over time. Any questions? I am going slightly slower than I was hoping because the next subject we're going to do is to do some basics of special relativity. It is a reminder of special relativity, but it's also, you need to get used to the concept of 4 vectors and 4 momentum and the way I derive the way I write covariant derivatives, etc. So now we're starting to get slightly more technical. But there are still a few things that I said that are going to be much less technical before we dig somewhat deeper. So I was actually hoping to begin special relativity today, but that did not work out. Again, one thing I can control is how quickly I'm going. If you want, I can go faster. Does anybody want me to go faster? Oh, very quiet. Does anybody want me to go slower? Also very quiet. Okay. Any last questions? Any final questions?
I think the stuff will get a better idea when you actually start the maths. We'll get a better idea of the speed. Today was very like, you know, history.
Okay,
So
no, that was just an introductory, just to give you a broad overview. But in some sense, this course will give you an overview, because there will be things, as I told you, unfortunately, I will not be able to go through the full details. All right, then I think it's time to end this session, and then I'm going to see you again on Thursday. Since I haven't had really time to start special relativity, I might just use the 2 hours on Thursday to discuss the special relativity rather than to do a tutorial, because the tutorial is on special relativity. So that means we might just start the tutorials next week, as I told you. Good. More? No? I told you I'd give you a little bit of a homework. Go read the Griffith chapter 1. It's just an historical overview. There are no any equations or anything in there. But it gives you some nice summary of some of the ideas, and there is some discussion about some of the symmetries that are involved. And you'll notice that there is one Israeli that is mentioned there. This is Yuval Ne'eman. He was quite famous in that subject in the 1950s and early 60s. Though it turned out that his theory was not as good as those of Murray Gell-Mann, who did the symmetry slightly better and then got a Nobel Prize for it. All right. If nothing else, then thank you very much. And I see you all on Thursday at 2 p.m. Now you'll see there is a connection in the, well, you already saw because you came here. There is a connection in the course's website, on the webpage. So see you all there.
Thank you.
Thank you very much.
Thank you very much. Goodbye.
Bye-bye.